Hi everybody, this video will cover section 5 of chapter 3, rational functions. In this video we're going to talk about, yeah, you guessed it, rational functions. These handy dandy little limiting lines called asymptotes, and we're going to use those as a tool for graphing rational functions. Okay, so what is a rational function? It is really nothing more than a ratio of two polynomials. Here, p of x is a polynomial, this kind of stands for product. Here, q of x is a polynomial, kind of stands for quotient, I suppose. And if you take the ratio of those two, you have a rational function. Perhaps the most basic rational function is called the reciprocal function. It's basically equal to the ratio of the polynomial, p of x is equal to 1, divided by the polynomial, q of x is equal to x. Here are some of the tables, and as you can see, they are reciprocals, and here is the graph of the function. Notice that this vertical line here on the y-axis is we call the y-asymptote. This basically shows the value of x where the function begins to approach either positive infinity or negative infinity. And then here we have the horizontal asymptote. Now, not all rational functions will have a horizontal asymptote. Sometimes it might be oblique. Sometimes there may not be an asymptote at all, except for the vertical asymptote. However, in this particular case, we do have one, and it kind of shows the value. It shows what the function approaches as x gets to infinity or negative infinity. What else can we say about this function? Well, notice here that the domain is the entire real line with the exception of the one point where it is undefined. So it is the open interval between, so it's the entire real line except 0, which of course we write as this, the open interval from negative infinity to 0, unioned with the open interval from 0 to infinity. That's how we show that it's every single point except 0. The range is the exact same thing. Why? Because as x approaches infinity, the function does approach 0, and it gets very, very close to it, but it never actually touches 0. Does this function ever increase? No, it does not. It is always going down. You could say that it is always getting down. It will never, ever go up. As a consequence, it is increasing upon the open intervals negative infinity to 0, and then from 0 to infinity. Of course, it's not decreasing at 0 because it is discontinuous at 0. What else can we say about this? Well, as I mentioned before, it has a vertical asymptote. And that is the line at x where the equation approaches, where the function approaches either positive infinity or negative infinity. And there is a horizontal asymptote at the x-axis, which basically shows that as x approaches infinity, the function approaches 0, but never quite touches 0. And also you will notice that this is an odd function. It actually satisfies the requirement f of x being equal to the negative of f of negative x. For example, here we have 1/2 and 2. And over here we have negative 1/2 and negative 2. As a consequence, it is symmetric about the origin. Okay, perhaps the next most basic function is the reciprocal function squared. And here it is. Once again, here's a plot of some of the points for it. And this is what the sucker looks like. It turns out the asymptotes are the same. It is still undefined at 0. It approaches infinity. The function approaches infinity as x approaches 0, and the function approaches 0 as x goes to infinity, which gives us the horizontal asymptote. It turns out that the domain is the same, and you can sort of see that here, but the range is different. Since we're squaring, we have no negative values. As a consequence, the range is from 0, not including 0, all the way up to infinity. And now this function actually has an interval where it's increasing. And of course that is all the negative values. All the values from negative infinity all the way up to, but not including 0. And it's also decreasing from 0 to infinity. But there is still a discontinuity at x equals 0 because once again it is not defined at x equals 0. The vertical asymptotes happen to be the same. The only primary difference here is, now check this out, this function is not symmetric about the origin anymore. It's now only symmetric about the y-axis. As a consequence, this function is even. So we have odd, and we have even. And this brings us to our first example. I'm going to throw it to you all at once, and here it is. We want to graph f of x equal to 1 over x plus 2, the entire quantity squared, minus 1. Well, notice that this is really nothing more than our base function translated to the right by 2 units, the x plus 2, and then down by 1. So this is an exercise in 3.5 and 2.7. And what we want to do is give the domain and the range, plot the largest interval where it's increasing and largest interval where it's decreasing. And of course, once you see the plot, it's pretty straightforward to do. The domain, well, since this is nothing more than a shifted version of this particular function, it is going to be, the domain is going to be shifted to the left as well. So it's going to be the open interval from negative infinity to negative 2, not including 2, and then the union with the open interval from negative 2 to infinity. So basically every point on the real line with the exception of 2. And now since we are shifting down, the range is going to shift down, and now the range is going to be from negative 1 all the way up to infinity. When is it increasing? Well, thanks to the shift left term, it's going to be increasing from negative infinity to 2. And where's it going to be decreasing? Well, once again, because of the shift, it will be decreasing from negative 2 all the way down to infinity. And of course, you can always get all this stuff when you have a graph that you can look at. And that is all that we have for this one. If you were asked about the asymptotes, well, then the asymptote will be the vertical line of x equals 2, and then it'll be the horizontal line of y equals negative 1. And that brings us to, you guessed it, asymptote. So let's suppose that p of x, or the p and q are polynomials. Okay, and we're going to let f of x be the ratio of p and q. However, it's going to be reduced into lowest terms so that basically the denominator and the numerator and the denominator will not have any common factors other than 1. If that's the case, then we can define the vertical asymptote as the line x equals a where f of x approaches infinity. So if f of x approaches infinity, if the absolute value of f of x approaches infinity, like down here or up here, as x approaches a, then the line x equals a is known as a vertical asymptote. Now our example here, we actually have 2 vertical asymptotes because there's 2 points where the function actually approaches either positive infinity or negative infinity. Okay, number 2. If there is a horizontal asymptote, there isn't always has to be one. So if f of x approaches b as the absolute value of x approaches infinity, so either in this direction or that direction, then the line y equals b is a horizontal asymptote. Now, not all rational functions have a horizontal asymptote. Some actually have what we call an oblique asymptote. And we will talk about how to figure that out. Matter of fact, I think we'll do that right now. Oh, no, we're not going to do that now. We're going to show you an example. And here it is. Once again, for this particular rational function, we have one vertical asymptote at x equals negative 1 and another one at x equals 1. And here we do indeed have a horizontal asymptote at y is equal to b. Okay, well, how do we figure these things out? Well, vertical asymptotes are pretty straightforward. First, vertical asymptotes would ever occur when the denominator is equal to 0. And that occurs with the polynomial, and that occurs at all the zeros of the polynomial in the denominator. As a consequence, we just set the denominator equal to 0, solve for x. All those solutions will have, or are going to be the x values for our vertical asymptotes. Now, if you solve for x and you get no real valued solution, then there is no asymptote, because we are only restricting ourselves here to the real line, or to real numbers. Okay, well, what about other asymptotes? Well, it turns out that if the degree of your numerator is less than the degree of your denominator, you will always have a horizontal asymptote at y equals 0. If the degrees are the same, then you will have a horizontal asymptote at the ratio of your leading coefficient in the numerator and the leading coefficient in the denominator. And if you think about it, it kind of makes sense. For example, suppose here that x goes to infinity. Well, then this term is going to get very, very large, and this term is going to get very, very large, much larger than, say, a to the n x to the n minus 1 term, and much larger than the linear term, or even the quadratic term. As a consequence, as x goes to infinity, f is going to approach a sub n x to the n over b sub n x to the n. I mean, we'll still have these other values, but they'll be so small they'll be of little significance. As a consequence, these will cancel, and this will approach a sub n over b sub n, which is actually why we have our horizontal asymptote here. Okay, well, what if the degree is 1 more than the numerator? Well, then you're going to have an oblique asymptote. And that oblique is basically had the equation of a line. So it's going to have the form y is equal to mx plus b. How do you find that? Well, you take your numerator, divide it by your denominator, or by your denominator. You are going to get some quotient, and then you're going to get a remainder. Just discard the remainder. Your y asymptote will be that particular quotient. And since p is 1 degree higher than q, this will be a line. And this brings us to a couple of examples. And here is the first one. Here we want to find the horizontal, vertical, or oblique asymptote of, in the first case, 4x minus 2 divided by x plus 1. Okay, so how do we find our vertical asymptotes? Well, we set the denominator equal to 0. So that will be x plus 1 is equal to 0. And that corresponds, when we solve that, we have that x is equal to minus 1. This right here is our vertical asymptote. Okay, the horizontal asymptote? Well, since they are of the same degree, the horizontal asymptote is going to be y is equal to the coefficient next to the linear term, 4 divided by the coefficient next to the linear term in the denominator, 1, or just y is equal to 4. That's the Laplace arrow. Y is equal to 4. Can you see that? Well, yeah, because remember, as x goes to infinity, well, I mean, the 2 and the 1 are going to stay the same, but this is going to get large. This is going to get very large. So this is going to approach 4x over x, or 4. And that's how we get that. Now, what does that look like in a graph? Well, here is our equation. Here is our vertical asymptote at x equals 1. You can sort of see it here. And then here is our horizontal asymptote at y is equal to 4. And there you go. That's pretty much what they look like. Okay, what about the next one? Okay, here we have x squared plus x divided by x minus 1. And as you can see, we have the degree of the numerator is 2. The degree of the denominator is 1, so this is going to have an oblique asymptote. But first, let's take care of the vertical asymptote. Okay, the vertical asymptote we can find by setting the denominator equal to 0. That is, x minus 1 is equal to 0, and that corresponds to x being equal to positive 1. Okay, for the other asymptote, notice that this is 1 degree higher than the other, so we are going to have an oblique asymptote. Yeah, okay, cool. All right, and that means we need to divide the numerator by the denominator. And to do that, and actually since we have an x minus 1, we can go ahead and use synthetic division for that. So since I'm doing x minus 1, I'm going to have a 1 here. And then my quadratic coefficient is a 1. Hey, my linear coefficient is a 1. My constant is a 0. Draw my line down here, bring my 1 down. 1 times 1 is 1. Love that rough math. 1 plus 1 is 2. 2 times 1 is 2. 2 plus 0 is 2. I'm surprised I had to think about that. Okay, that basically means that we're going to have a quotient of x plus 2, and then a remainder is 2, so this is going to be plus 2 over x minus 1. We don't care about this. We just have that. We just want to care about the quotient, and this right here is going to be the equation for our oblique asymptote. That is going to be y is equal to x plus 2. Okay, well, let's go ahead and see what that looks like. This right here is our rational function, and notice this funky little shape going on here. Okay, well, once again, here's our vertical asymptote. Here's our vertical. There it is. X equals to 1 right there. And then here is our oblique asymptote. And notice how as x goes to infinity, the function approaches this particular straight line. Okay, so that's what this fun, and that's why this asymptote happens to be vertical. The question here is, well, what would happen if this was like an x cubed? So we actually had something that was more than a degree higher. Would we have an asymptote? Let's find out. Let's change that. Actually, let's go ahead and change it to fourth. And there you go. And the answer is no, you won't. The asymptote goes away. Instead, this has more of the behavior of what you would find from a standard polynomial. This actually behaves as basically x cubed as this goes high. Now, ironically, if you change that to a third, then now notice the signs shift because as x gets large, this behaves like as x gets large, this behaves like x cubed over x or x squared. So everything is now positive. Okay, so what do we have next? Okay, next we want to talk about graphing rational functions. And I have a handy-dandy 7-step process for you. First thing you want to do is find any vertical asymptotes, and now we know how to do that. Secondly, we want to find any horizontal or oblique asymptotes, assuming, of course, that they exist. Then we want to plot the y-intercept if you can. Of course, if the denominator is equal to 0, when x is equal to 0, you cannot plot your y-intercept. And then we want to plot any x-intercepts, and of course, so those x-intercepts will be the zeros of the polynomial in the numerator. Then you want to determine whether your graph will intersect its non-vertical asymptote. Even though the value of your function may approach these asymptotes as x goes to infinity, there are still finite values of x which actually might cross the asymptote, and you can find that essentially by setting f of x equal to b or mx plus b for the oblique case, and seeing if you get a solution. If you get a solution, then obviously the function intersects. If you get something that results in a contradiction, like you solve it and you get 3 is equal to 4, well then there is no solution and they do not intersect. Once you've done that, plot those points. Once you've done that, maybe you want to plot some more points. So plot the points as necessary, and then maybe plot some more. And once you've done that, you can actually complete your sketch. So let's go ahead and do that. Now in your homework, you will not be required to create a graph, but you are going to be required to actually look at a graph and recognize which equation from a collection of equations actually correspond to that graph. And of course you would do that by mapping the asymptotes that you see on the graph to the asymptotes produced by the equation and so forth, and also the intercepts as well. Okay, so here we have 3x squared minus 3x minus 6 all over x squared plus 8x plus 16, and we need to graph that, and we're going to do this in OneNote. Okay, so the very first thing that we want to do is, well, find the vertical asymptotes. The asymptotes are those values of x where the denominator is equal to 0. So for vertical asymptotes, we want to find those values of x where x squared plus 8x plus 16 is equal to 0. All right, well, if you take a look at this, you know that there's two solutions because it's a quadratic. And also, if you look at this, it's actually factorable. Matter of fact, if you look at this even closer, you can see this has the form of x squared plus 2 times 4 plus 4 squared. This right here is a perfect square. This can be written as x plus 4, that's not a 4, x plus 4, the entire quantity squared, is equal to 0. As a consequence, we have a vertical asymptote at x equals to 4. So, and there's my vertical asymptote. That's better, and let's move this graph. So there we go. So there's a vertical asymptote. Now we need to find all of our horizontal asymptotes. Well, okay, if there are horizontal or oblique asymptotes. So Well, notice we have a degree of 2 and we have a degree of 2 here. So basically, our horizontal asymptote is going to be y is equal to the coefficient next to the 3, or the coefficient in the quadratic term in the numerator, which is 3, divided by the coefficient in the denominator, in the quadratic term denominator, or 1, or equal to 3. And once again, as you've noticed, if x becomes very, very large, these terms become much more dominant compared to the other terms. So this would approach 3x squared over x squared for large values of x. And of course, these would cancel, and you would have 3. So there is a horizontal asymptote at y equals 3. And here is our horizontal asymptote. Okay, now you want to evaluate this function. We want to see if you can compute the y-intercept, and in this particular case, we can. And we find the y-intercept by setting x equal to 0 and evaluating the function. If we do, we get negative 6 over 16, which reduces to negative 3/8. So we have a y-intercept at 0, negative 3/8. And that is right here. To find our x-intercepts, we want to find all the zeros of the numerator. So that is solving 3x squared minus 3x minus 6 is equal to 0. Okay, if you can see here, we can factor out a 3, or we can divide everything by 3, and that will give us x squared minus x minus 2 is equal to 0, and that factors into x minus 2 times x plus 1 and then the solutions here will be x is equal to 2 and x is equal to minus 1. So that means we are going to have x-intercepts at 2, 0, and then negative 1, 0. And where would those be? Well, this will be 2, 0 right there. And then here is negative 1, 0. Now we want to see if our graph is going to intersect the horizontal asymptote. Okay, so to do that, we actually have to set the equation equal to y is equal to 3. So that is going to be 3x squared minus 3x minus 6 divided by x squared plus 8x plus 16 is equal to 3. We need to solve this equation for x. And if we do that, we can do that by getting rid of the fraction, and that will give us 3x squared minus 3x minus 6 is equal to 3 times x squared, which will be 3x squared, 3 times 8x, which will be 24x, plus 24x, then 3 times 16 is plus 48. Now we can do some simplification. These cancel. I can add the 3x to both sides, and that will give me negative 6 is equal to 27x plus 48. I can subtract 48 from both sides, and that will give me negative 54 is equal to 27x. Divide both sides by 27, and I have that x is equal to negative 2. Okay, so it turns out that our equation is going to intersect the horizontal asymptote, and that is going to occur at negative 2, 3, which is this particular point right there. Okay, so it might be good to plot a few more points. If you've noticed, I kind of have a good idea of what's going on here, but I might want to plot a few more points over here. So how about if I plot f of 9, evaluate f at 9? Well, if I do, I will find that this is equal to 10.5. And then if I evaluate this at, that's f at negative 9. And if I evaluate f again at negative 10, which I want to do because I have no points over here, I will get the value of 9. So now I can go ahead and plot those 2 points. Let me zoom this thing over here. And I'm going to go ahead and make this bigger. And so here is negative 9, 10.5, and here is 10, negative 9. And now this gives me enough to graph it, because I know this is going to kind of go like this. This is going to come all the way down over here, and then go like that, because it's going to approach -4. And if I do connect the dots, I might want to do a few more plots over here. It's going to look like that. And if I zoom out, see, here is our vertical asymptote, here is our horizontal asymptote, and here is where it crosses the horizontal asymptote. So that is a possibility. Okay, so this brings us to another example. Now here we want to graph 2x plus 1 over x minus 3. So let's go ahead and do that one. First I'm going to copy this and put this in OneNote. Okay, and here we go. Let's start off with our vertical asymptote. Okay, and we can find that by setting the denominator equal to 0, and we find that the vertical asymptote is x is equal to 3. Okay, cool. Give me 1 second. Let me get my other. Okay, we're done with this one. Let's look at this one over here. So x is equal to 3. There's our vertical asymptote. For our horizontal asymptote, for any other asymptote, notice that the degree of these two are the same. So the horizontal asymptote will be at y is equal to the ratio of the coefficients, or just y is equal to 2. Oh, and there it is. It's already there. How convenient. Now we want to figure out where the y-intercept is. Okay, well, that's just f of 0. And f evaluated at 0 is going to be -1/3. So the y-intercept will be 0, -1/3, which is right down here. Okay, and now we are going to determine now the x-intercepts. Well, since this is a linear equation for the numerator, there's going to be exactly one x-intercept, and that's going to occur when at the 0 for a linear term, and that will be when x is equal to -1/2. So that the x-intercept will be -1/2, 0, which of course is right there. Of course, I didn't realize you can see them all. See all the points right here. Okay, so now we want to determine whether or not the graph is going to intersect our non-vertical asymptote. And of course, to figure that out, we need to see if we need to solve this equation for y equals to 2 and see what we get. So, and to do that, we will set 2x plus 1 over x minus 3 equal to 2. If we do, we will have 2x plus 1 is equal to 2x minus 6. Do 2x's cancel, and we have that 1 is equal to -6, which makes no sense, so it does not cross. Okay, so we have basically our asymptotes, we only have 2 points, so it might be a good idea to do a few other points. So it turns out, so let's go ahead and do that. It turns out that for if you evaluate the function at 4, you get 9. That's this point right here. If you evaluate the exact same function at 8, you'll get 3 2/5 or 3.4. Okay, that is this point right here, 8, 3.4. If you evaluate the function at 2 right here, you will get -5. So 2, -5 is that point down here. And then if you evaluate this function at -4, you will get a response of the output will be 1. So you'll get -4, 1, which is this point right here. So now we probably have enough points, let me make this graph bigger, to actually graph this function. And you can see there'll be a line that goes kind of like this, and then another line that goes kind of like that. And of course, with the help of GeoGebra, that's what your graph should look like. And this brings us to our last example. Here we want to graph x squared minus x minus 6 divided by x minus 3. And notice that this is a rational function that is not expressed in lowest terms. So let's bring up our combination of GeoGebra and Notepad, or OneNote, and let's see if we can figure this out. Well, since it's not expressed in lowest terms, that means they have a common factor. So we can actually factor out the numerator to see what that might be. Okay, so if you notice here, the numerator will easily factor into the products of x minus 3 times x plus 2. And that, of course, the factors, and of course in the denominator we have x minus 3, and this is how it factors. However, since this function has a x minus 3 in the denominator, right here, this function is still not defined at x equals 3. Since this function has x minus 3 in the denominator and will be equal to 0 when x is equal to 3, this function is not defined at x equals 3. 3 is not an element of the domain of f. Every other number is, but not 3. Okay, with that in mind, we can go ahead and factor this out, and this factors into x plus 2. Okay, as a consequence, the graph of x plus 2 is basically a line, y-intercept of 2, and a slope of 1. And here it is. However, since this function is not defined at 3, because x minus 3 will produce a 0 in the denominator, we actually have to exclude that point x equals 3, or the point at the point x equals 3, or 3 comma 5. That point will not be on the graph, so this right here would be the graph of the function. Basically the entire real line, or the entire line y equals x plus 2, with the exception of the point 3 comma 5. And that is all I have for this particular section. If you have any questions, please reach out to me. I'm always happy to help any way that I can. And this is Bob Boyle, signing off.